Welcome back to Part 11. In our last session, we explored the mathematical theory behind cut sets and learned how Boolean algebra helps us isolate a system's most fundamental vulnerabilities. Now, it is time to put those concepts into practice. We are back inside the Item Toolkit workspace with our reactor vessel model fully constructed and quantified. In this section, we will execute the calculation engine and extract our primary risk metrics. We will navigate the results interface, examine our system's actual minimal cut sets, and analyze how the software ranks these critical failure scenarios. By the end of this video, we will know exactly which combinations of events pose the greatest threat to our defense in depth, allowing us to make informed, data-driven safety decisions. Let's dive right in. Before we run our analysis, we first need to define the system's operational lifetime. This parameter tells the calculation engine exactly how long of an exposure period to consider when computing our overall system unavailability. To set this, navigate to the dialog view at the bottom of the workspace and update the system lifetime field to 8,760 hours, which represents a standard one-year operational mission profile. With our time frame established, we are ready to quantify the model. To execute the analysis in the Item Toolkit, simply click the Go button located on the main toolbar. The calculation engine will process our logic immediately. Once the calculations are complete, an advisory dialog box will appear to notify you of any structural or mathematical errors. As you can see on our screen, our fault tree analysis has completed successfully with 0 errors. Click OK to close this prompt and return to the main canvas. If you look closely at the diagram, you will now see that the calculated unavailability, denoted by the Q value, is actively displayed beneath every single basic event and logic gate in our tree. If we look at our top gate, we can see a calculated unavailability of 0.000638. This tells us that the probability of our safety system being unavailable and failing to protect the reactor during our one-year operational profile is exactly 0.000638. While seeing this top-level number on the canvas is helpful, we need to understand exactly what is driving that risk. To view the detailed breakdown, click the Results Summary button located on the main toolbar. This will open the comprehensive results summary window. This interface is logically organized to help us navigate our quantitative data. On the left side, you will see a hierarchical list of all our gates, allowing you to select and isolate the results for any specific subsystem in your tree. The right side of the screen is split into 3 distinct panels. Top panel, Summary View. This displays the high-level quantitative metrics, including unavailability and failure frequency, for the gate you currently have selected. Middle panel, Importance Measures. This area calculates the specific risk impact of our individual components. We will be exploring this panel in much greater detail in our upcoming sections. Bottom panel, Cut Set View. This is the area we want to focus on right now. This panel lists out the minimal cut sets that the software has mathematically extracted from our fault tree logic. Before we dive into the details of the cut sets, take a look at the gate hierarchy on the left side of the window. You will notice that currently, only our top event, G explosion, is listed. This is because, by default, the Item Toolkit only calculates and stores the results for the top gate in order to optimize computation time for large-scale models. If we want to evaluate the metrics for our intermediate subsystems, we need to instruct the software to store that data. To do this, close the Results Summary window and navigate to the top menu. Select Analysis, then retain results for all gates, and choose Current System Only. This action turns on the quantitative retention flag for every intermediate gate in our model. A dialog box will pop up confirming that results will now be retained for all gates. Click OK to close this prompt, and then click the Go button on the toolbar to run the analysis one more time. Now, when we reopen the Results Summary view, you will see that every single gate in our fault tree is listed alphabetically in the left-hand hierarchy. You can now click on any individual gate to instantly view its specific unavailability, importance measures, and cut sets. Let's select our top gate, G explosion, from the hierarchy on the left to examine its specific cut set data. Looking at the summary view in the top panel, we can see that there are 11 minimal cut sets in total for this top event. Down in the bottom panel, these 11 cut sets are listed and automatically sorted by their unavailability, ranking them from highest risk to lowest. The table provides key metrics for each cut set, including its overall unavailability, expected frequency, order, and the specific list of basic events that create the failure path. The order of a cut set simply indicates the total number of individual basic events that make up that specific scenario. If you look closely at our list, you will notice that every single cut set has an order of 3. This mathematical output perfectly validates the physical architecture of our reactor vessel, directly mirroring the 3 independent layers of defense in depth we engineered into the system. Let's examine the highest risk cut set at the very top of the list, which consists of 3 specific events occurring together: EV2, MV2, and NRV. This scenario maps perfectly to a total bypass of our safeguards. EV2 represents a failure in our first line of defense, the automated electronic protection. MV2 represents a failure in our second line, the manual human protection layer. Finally, the NRV represents the failure of our last resort, passive mechanical relief valve. If all 3 of these specific protections fail simultaneously, the vessel will explode. In any well-designed safety architecture, the most critical vulnerability you want to eliminate is the single point of failure, a scenario where just one component fault brings down the entire system. The cut set view provides a clear, immediate way to identify these paths. If a single point of failure exists in your model, it will automatically show up in this list as a cut set with an order of 1. Because all of our cut sets currently have an order of 3, we have mathematically verified that our baseline design successfully avoids any single points of failure. However, our analysis isn't quite finished. In our next section, we are going to link our external power grid back into the fault tree. We will study exactly how introducing a shared power supply impacts our cut set results, and explore what that means for the overall reliability of our system design. Thank you for watching, and I will see you in the next part.